All right, so we're going to start this concept of radicals again, but now specifically with binomials. So we've looked at radicals before. We've done this in language has with square roots, and cube roots, and fourth roots, and we rationalize the denominator itself. We're going to continue with that concept here, but we're going to start generally with the term binomials containing radicals, and then we'll get into rationalizing those denominators again. So the simple rule, and it's really not a rule, it's almost common sense when you get to the problems you see, is that if you have a binomial times a binomial, we need to FOIL it out. You can introduce yourself.
Oh, sorry.
That's all right.
This is
you
Chris.
put on the spot. Chris? Chris, where are you from?
Al Stevenson.
Where is it?
Al Stevenson.
Okay, cool. You like math?
Yeah.
Okay. Is that an answer you're going to give to any math teacher, or is that an honest answer?
Yeah. That would be
Oh, okay. So the rule is just FOIL. You're going to have two binomials, treat them as if they're variables. So x plus 2 times x minus 3. How would you multiply that out? You're going to do the same thing here, but now with radicals containing binomials containing radicals. So look at the first example. Just do part A. I want you to figure out the trend as we go through this. We'll start with part A first. And part A is just a practice. Okay, it's just a practice. Remember, outsides multiply outsides. Insides multiply insides. So again, if you're having trouble and you're not sure, think of this as 4 plus x times 5 minus x. Okay, think of that right now. We do the same thing you would do. The reason I call them both x's is because we go radicals with. If the radicals had been different, like in this problem, this one, I'm going to use x and y instead. So I just wrote it out in color so you can see the actual thing. Again, recognizing that integers multiplied by irrational numbers like radicals cannot be multiplied. You just literally put them next to each other, right? So this topic is not that hard because you're literally just lining up the values. 4 times negative root 3. Well, it's negative 4 root 3. You don't have to actually do any multiplication here. Obviously, these are like terms now, so you can combine the middle terms, right? This is like negative 4x and positive 5x. I'll combine those two things. So we'll do that to start. So we'll say here that we have a positive root 3 in the middle now as a result of these two being added together. And then I really have 20 minus 3, which is 17. Again, this is really 3 right here. So I have 20 in the beginning in red. This 20 here minus 3. So put a 17. So what do you recognize? What do you pick up on? When you multiply two things that are binomials with radicals, what's your result going to be? What's your result going to be? Binomial with radicals. It's not like when you FOIL it out and you get a trinomial, right? You recognize the difference here? Okay, with the trinomial, then we have to consider the fact that we have 3 terms. We only have 2 terms here. This is really interesting, and then we're going to get even further with this idea. To the idea of like, if you look at part D, if you want to look ahead, you can idea what we're going to do. Okay? If you're good with that, we can jump to part C, because part B is really kind of the same thing. It's kind of a waste of time to do. Yeah?
Where is 17?
So the 17 comes from the integer parts, and this is 20 here, and that's minus root 9. But root 9 is 3. So the integer components are 20 and a negative 3 yielding 17. And then the non-integer components, right, the irrational parts in the middle, also get summed together. It's kind of like terms, right? Think about like terms when we do this. So I'll write down what part B looks like. Okay, I'll just write it down so you can check your work if you've done it already. So we're going to have the first term, we're going to have 3 root 2. The outer term, and I'm just doing it in order of FOIL so you know the direction I'm going in, but you don't have to, obviously. You can double distribute the way we've shown. The second part, the outer part, is going to be a positive 4, and then it's root 2 times root 2, which is root 4. Again, I'm multiplying these two quantities, this and this right here. Okay, these two quantities I'm multiplying. That's the outer part. Then I go to the inner part, and I get a negative 18 from that. And then I go to the last part, which is this negative 6 times 4 root 2 over here on the right. Okay, those two quantities multiplied by one another. trying to use the cursor at the same time in two spots there. So that's going to be a minus 24 root 2. And then all I have to do here is simplify. And recognize that whenever you multiply a radical by itself, you're always going to end up with a perfect square. So when you pick up on it after a while, you don't have to write out root 4. I'm doing this because it's the first time we're doing this lesson. But root 4 is clearly 2. And 2 times 4 is clearly 8. So you could have just written this as 8 if you did the math in your head. Just like this, obviously, write that as a 3. Yeah, I'm just showing you the steps for this. So we've got this here as an 8. Okay, an 8 minus 18 is a negative 10. Okay, I've got an 8 here, minus 18. That gives me the negative 10 there. And then finally, at the end, I've got 3 root 2 minus 24 root 2. How many root 2's is that? 3 root 4 minus 24 root 2. What do we put as an answer for that? Negative what? 21 root 2. Okay, again, that's coming from here and here together. Just be careful of your signs. The common mistakes I see are that people forget to carry the signs over with each piece. Thank you. Part C, when you see a squared term, what will make someone turn over in their grave? Or have you heard that saying before? It's usually someone who's passed away, though, actually. It doesn't make sense. What would be the common mistake here? What would be the common mistake for part C? A lot of you have done it, actually, and a couple of you did it. I think you got on the test. Yeah. Yeah, to distribute the power. That would be the common mistake. This is a binomial like x plus 2, right? If I had x plus 2, that whole quantity squared, it's really x plus 2, right? You're really just foiling this again. So just recognize that here, just get rid of the square if you want, and just rewrite the same thing if it helps. And when we do this, we're going to pick up on that trend again. It is going to follow that trinomial rule, but because the first and last terms are going to be integers, it's not going to be as useful to use this. Remember the rule we had? When you squared something like a sum, like x plus 2, if you squared it, it automatically became x squared plus 4x plus 4.
Can you do the thing where you square the first term and you do minus 2a?
You got to listen. That's what I just said, Mark. I just said that. So I said you can do that, but it's not as useful here. I was just saying this because the first and third term become integers, right? So as a result, those combine anyway. So you can apply the rule if you want, which is fine, but then you're going to have to simplify beyond that rule, okay? It's a good question, but I was answering that question as you were thinking the question. So when I multiply this out, I'm going to have 2 root 3 times 2 root 3 is going to be 4 root 9 for the first one. Outer is going to be negative 8 root 15. And again, take a look. Outer multiplies outer. So when I'm multiplying these things, I have to take the 2 times the 4 first here, and then the root 3 times the root 5 second over here. Is that clear what I'm saying, right? Or I'll refer to this? Outer and then inner. Multiply them correspondingly, if you will. And then the inside part here is going to be the exact same thing. Another negative 8 root 15. And then finally, the last part is going to be a positive. We're going to have 16 times root 25. And then just simplify. So see how the first and third are integers there because the perfect squares now? So that's 4 times 3, which is really 12 here. This is minus 16 root 15 when I combine those two. And then this is plus, what's 16 times 5 give me? Quick mental math, 16 by 5. 80? Close?
Oh,
yeah. And the easy way to do mental math like that, right? 5 times 10 and 5 times 6, add them together. 50 and 30 is 80. And then combine like terms here. 12 and 80 is going to give me 92 minus 16 root 15. Okay, again, this is not like a mind-blowing topic at all, right? It's just following the rules. Make sure you FOIL. Make sure you combine like terms properly. Whenever you have a radical times itself, you're always going to get a perfect square, and it's always going to reduce. So it's the same process over and over.
Wow, wait, how did you get 16 root 15? Wait, is that from the
Root 25. Oh, here you mean? Here? It's the combination of these two.
Oh.
Negative 8 root 15 plus negative 8 root 15 is negative 16 root 15. I'm adding the no terms together. Okay? They're both negative, so adding two negatives makes it more negative. All right, so we've got A, B, and C. How about D now? If you've just looked at D, I mean, some of you already got ahead, I know that, but if you've just looked at D or you want to talk about it, what could you say about part D that's going to be different about that from A, B, and C? Did you already do it more out of curiosity? Did you get through it? What do you think is going to be different, or what do you suppose is going on here more? Good. It's a difference of two squares. That's the one thing I want you to pick up on. Let's write this word down now. These are called binomial conjugates. And I've used that phrase before. I've talked about conjugates. When you have x plus 2 and x minus 2, we would say that they're conjugates. And these are binomials. So these are called binomial conjugates. Okay? And that always is the case when we have two things that only differ by the sign between them. Now, when I multiply these out, think about what's going to happen. When you multiply out x plus 2x minus 2, what happens to the middle terms? They cancel down. So here the middle terms are going to cancel out. And the middle terms are the parts that have the radicals left. So we're not going to have to worry about any radicals at this point. But the first term and the last term are going to be perfect squares. So the first and last term are going to simplify to integers. So our answer, we can predict, will be an integer, actually, which is really kind of interesting to think about. We're multiplying two things that are completely irrational, and yet we're getting a rational answer. Right? It's like root 3 times root 3 gives you root 9, and that's rational now, right? Two irrationals can make a rational if you multiply them. So when we do this, let's go through the process, but I want to show you how the middle terms are going to cancel here. So when I multiply, I get 2 root 5 times 2 root 5 is 4 root 25. Outer is going to be 2 root 5 times 3 root 7. That's going to be a positive 6 root 35. Inner is going to be negative 3 root 7 times 2 root 5. That'll just be the opposite of that, which we expected to happen. We can already put a line through them. Cancel, cancel. It always happens, right, when we multiply conjugates with one another. And then the last term is going to be negative 3 root 7 times positive 3 root 7 is negative 9 root 49. And clearly here we have perfect squares. We can simplify. This becomes 4 times 5, which is just 20. And this becomes 9 times 7, which is 63. So here's our answer. So when we have binomial conjugates multiplied, we get a rational answer, even though we started with irrational numbers. Stay with me now. So, in the last section, we had a problem with having radicals in the denominator, right? Do you remember that? We said you can't have radicals in the denominator of your answer. And I talked about how that's kind of ridiculous, really. It doesn't really matter, but it's a good technique to learn. This is the real important technique now that we're about to see, okay, that you're really going to have to use in calculus and later on in math. So the concept I want you to think about is now, what if we have some number in the numerator, right? And that's over a binomial conjugate like this. Oops, I don't want to put the radical there. I want to just extend that line. So this is clearly an irrational denominator. Radical C makes this irrational. How can I make this denominator now rational? What do you suspect I should do? Ellen? Be careful. Not itself. In the last section, we multiplied by itself. It's, what do we call it? What's the word? What did we just write down? It's the word we just used a little while ago. Conjugate. By its conjugate. Not itself, very close, but you have to negate the sign. So if I multiply this by b minus root c over b minus root c, now I know, and I'm guaranteeing myself, look what I'm doing, by the way. I'm guaranteeing that the denominator becomes rational. Because I just said a minute ago that when you multiply two irrational binomial conjugates, you get an integer answer, or a rational answer. So by doing this, I'm guaranteeing that I'm going to get a rational integer answer, or rational answer, I should say, it doesn't have to be an integer, but in the denominator, which means I have a rational denominator, which is the whole goal of rationalizing the denominator. So we're going to take this approach in the next example, but I want you to see where it comes from. So part D is what led us to this concept, right? We can see that that's where that comes from. So look at part A now. So let's multiply by its binomial conjugate over itself, because I always have to multiply by 1, just like a least common denominator I'm doing it. But look what I do every time. Please make a note of this. I'm putting parentheses on purpose because a lot of people forget to distribute the numerator. The single term, that's the 3 here, needs to get distributed to both of these terms. And this needs to be FOILed out. So I put the parentheses enough in the beginning to remind myself. Once I'm good at this, I don't have to do it anymore, right? Once I practice it enough. But maybe do it a couple times here and there on your homework and then eventually stop doing it. So then this is going to become what? 3 times 2 gives me 6. 3 times root 5 is simply 3 root 5. I can't do much more with the numerator, right? That's all I can do. I can distribute the 3. That's it. The denominator, I've got 2 minus root 5 and 2 plus root 5. The first term is 4. Do I have to do the outer and inner terms? Why not, Helen? Yeah, they cancel each other out. Whenever, maybe write a note with an asterisk. Whenever you're multiplying things that are binomial conjugates, forget the middle terms. We do it all the time. When you have x plus 2x minus 2, you write x squared minus 4 right away. X plus 3x minus 3, you write x squared minus 9 right away. The middle terms cancel. So don't waste your time on them. Maybe make a note that we're ignoring them right now in this instance, in this circumstance. So I have negative root 5 times positive root 5 is negative root 25 there. And I can see that I get an integer denominator. This is 4 minus 5, which is really negative 1. So I'm going to write my final answer. Because I have a negative 1 in the denominator, I'm just going to negate the numerator and make it easier. Okay, I'd rather write my answer like this if I don't have to write it as a fraction on a 1. Make sense of what I did in the last step. The negative 1 is technically dividing into both terms. Remember this idea? We talked about this. When you have a monomial in the denominator and it's dividing into a binomial or polynomial, it divides into every term. Well, this 3 root 5 is one term. Remember? 6 is one term. So 6 over negative 1 is negative 6. 3 root 5 divided by negative 1 is negative 3 root 5. I don't put the negative on the inside. Are we clear on that? I cannot divide a number inside of a radical there. I'm not taking a number and dividing it into a radical. I should say an integer and dividing it into a radical. Questions on part A? Does that make sense? So do part B. Go ahead. Part C is the trickiest one, but they just get a little bit more difficult each time. There's more radicals. So just a lot of radical math, right? Go ahead and do part B. Yes, as well.
Would you have to multiply by the conjugate since the denominator is not negative?
You still use the conjugate every time.
Oh, because you're trying, yeah.
Because the middle terms cancel with the conjugate, right?
Oh.
If you did positive, what will happen is you'd end up with just some radicals there still. You wouldn't get rid of the radical, which is the purpose. So always use the conjugate. You're going to be positive, then you make it negative. If it's negative, then you make it positive. Just pretty much switch the middle sign.
When you have 2 terms on the top, do you distribute both of them into both?
Yeah, remember how I put parentheses around stuff, right? So that's going to be FOIL in the numerator also. The numerator's got to be FOIL, or double distributed, whatever it is. And that's the reason for the parentheses, okay? I mean, just to remind yourself that you're doing that. And mathematically, this does not need parentheses. Here's the reason. You're taking an entire denominator, right? And multiplying by an entire denominator. That's the rules of multiplication. Then you multiply the whole thing by the whole thing. So technically, you don't need the parentheses, and you should still be distributing. I put them there as a reminder only more. So you don't need to actually have them. The denominator should take you literally 3 seconds, right? It's always square the first term, square the second term, put a minus sign. And I'm even going a little bit too slowly, right? 36 minus root 9 is just 33. And you should be able to kind of do that in your head. You don't really need to show all the work for that. But again, just be careful with your work. If you're going to make a mistake and then there's no work, then it kind of becomes a problem, right? Foiling the top, we're going to get 24. Outer is going to be negative 4 root 3. Inner is going to be negative 6 root 5. Jeez, this is messy. And last is going to be positive root 15. So unfortunately, it looks like the numerator really can't combine much, right? We're going to have 4 terms in the numerator. Maybe I could break up the 15 into 5 and 3, but it's still not going to be able to add to these nicely, so it's not worthwhile. What do you say?
I was going to say, can you make 15?
It's root 5 times root 3, right?
Yeah.
And then, like, technically you could do like this plus the root 3 in the front if they both have root 5 as the base. But it just doesn't make any sense anyway, you know? It's not like they'll actually combine nicely. So I would leave it like that. Okay, this same thing here. Right there. And the last part C. So don't let many radicals intimidate you. They're all binomials still, right? 2 terms, makes it a binomial. 2 terms, makes it a binomial. So you multiply by its binomial conjugate. It's no more difficult, just you have a lot of radicals now at this point. The denominator is going to become 3 minus 6, which is just negative 3. Okay, again, denominator, root 9 minus root 36, which is just 3 minus 6. Numerator we can FOIL. It's going to be a root 6 when I do the root 2 times the root 3 first. And then outer is going to be root 2 times root 6, which is root 12. Inner is going to be a root 7 times root 3, which is root 21. And last, we're going to have root 7 by root 6, which is root 42. Can I simplify this? Can I A? B, is it worth it? It really messes simplification if I wanted to push it. Maybe the same thing as last time, when Maura asked about the 15, right? So I could break up this 12 into what, really?
2 root 3.
Yeah, this will become 2 root 3 at least, which is nice. And then I can think of this as root 3 times root 2, and try to simplify those. It just becomes messy. You're going to have radicals on the outside of a radical, which you have to add to an integer. It doesn't make sense to do it. But it definitely makes sense to make this 2 root 3. 21 now, which is 7 at the end. 42. What's 42? 21 by 2. 7 by 6. No, right? 7 and 6 doesn't work because 7 and 6, 6 becomes 3 and 2. There's no perfect squares in 42. So it just makes sense to simply change this to a negative 2 root 3 instead. Okay? Because again, root 12 is root 4 by root 3, which is just root 2 root 3 itself. So this becomes your answer over negative 3. Remember I talked about last chapter or last section with the factors about how it's a lot of bookkeeping. I used the phrase bookkeeping because I was saying like you're just crossing stuff in, crossing stuff off, you're tallying things. Here again, it's just a lot of arithmetic here, right? You're just multiplying stuff over and over again. Just gotta be able to simplify it. It's not a difficult topic, but at the same time, there's a lot of room for error if you don't practice and you don't if you don't work with your integers and radicals together. See how this becomes different when I suddenly have this now. Now there's no coefficients at all except for the one that came out. Yep.
How would you know when to not simplify it?
When there's no perfect squares that can come out anymore, or there's no common radicals. So if I had hypothetically, right? Hypothetically. Let's say this was 5 root 3. Then 5 root 3 minus 2 root 3 is 3 root 3, and I would simplify that. So I need to look for things with like radicals. I can make this root 2 times root 3, and then they both have root 3's in them, right? And this would be root 2 on the outside, minus 2, all in parentheses, times root 3. It's like you're factoring out a GCF of root 3 out of both of these, you know what I'm saying? So it really would be like factor by grouping at this point. You could factor root 21 out of both of these if you want. I'll show you what it looks like, just so you can see. But you don't need to do this. So watch what I'll do. So this first term I'm going to write as root 2 times root 3. I'm going to write the root 6 as. Then I'll minus 2 root 3 from that. And then this one I'm going to write as, I'm just going to leave this, actually, I'm going to leave this as root 21. And I'll write this next one as root 2 times root 21. And this is all over negative 3. So what I'm saying is I could break stuff up so that I get common radicals, right? And then factor by grouping in a sense. But it's not going to simplify in this case. So I'll show you. So let's factor out a root 3 of the first term. It leaves us behind with root 2 minus 2. So I'm factoring out of this right here. Okay, I'm factoring the root 3 out of there. Then I'll factor out the root 21 out of here. And that becomes a positive root 21 times the quantity 1 minus root 2 all over negative 3. So now, hypothetically, if I did have the same terms here and here, it'd be nice, right? That's what factor by grouping is. When I factor by grouping, I look at the first group and the second group, and I have to end up with the same thing in both spots. But I don't. So I can leave my answer in red, or I can write it the way I have it down here in this red-blue mix. But it's the same answer in both cases. More, is that explaining the root 3, root 5 part in the last one? Because I didn't show that in the last one, but it's the same concept here. Yeah, go for it.
So do you have to like try to factor by grouping and see if they become the same thing?
I mean, unless a lot of the time with radicals, you're not going to be able to simplify with factor by grouping. You could try it, but I also just look at it in your head. You look at it, right? If you take out the root 3, what are you left with? Well, root minus a number. Here, you're going to be left with a number minus a root, which are different things. Now, obviously, I could switch the order of this and take out a negative here. Remember that whole idea? I can make this sign negative and flip these around. It becomes root 2 minus 1. But this is root 2 minus 2. So they don't match up. But I guess if you don't want to take a chance, then yes, try to factor by grouping and see if it works. Yeah? Okay. There's no more. That's it for today. So this is this section. So you guys have a little bit of time still. You have about 15 minutes. I'd say just get the homework done right now. Okay, 6-4. Unless you have your project, you want to talk to me about your project, isn't here right now, it's an easy time to talk about that. If you want to check stuff with you. Let me grab my laptop so I can check what I have, okay?